Hello, this is lecture 500,325,026 in the course Fixed Parameter Tractable Algorithms, or more precisely lecture 25, but it does feel like a much larger number of lecture happened already. I don't know why. Okay, so previous lecture we talked about lower bounds, and we are not quite done with this chapter in the book, but I felt that, continuing in this stuff have diminishing returns because the stuff is pretty technical and, the value is not great. So I decided to jump back to chapter 12, which is about Metroids. And Metroid are essentially set systems that rise naturally, usually out of graph problems, but also other stuff. And they have some interesting algebraic properties. So you can do a lot of interesting stuff using the algebra, which I think is quite interesting. So I thought I will, look on the stuff there. And this lecture, I think, would be mainly an overview of Matroids. And we probably will get to the FPT stuff in the next lecture. Okay, so what is a Matroid? And Matroid is yet another example in math where, you have some fancy name for something, but the fancy name for something is just because, you need a word, you need a name for things, so you come up with a name for things, right? It's not like the label really matters, but the label somehow sounds very fancy, right? Think about hyper edges or hyperplanes, or um, similar example, or hypersphere, right? All those things where you use a fancy word to define something very simple. So Metroid is similar. It's a set system. So you have a ground set U, and you have a family of subset F, and then we have a certain properties that are required on the set. So first we require that the empty set is in F, and the second thing that we require is hereditary. So if we have a set X that is an F, and Y is a subset of X, then Y is also in F. Okay, so those are, not too interesting properties. I think if you have the first two properties, this is sometimes called the lattice. What makes Metroid interesting is that it has the third property, which is, think about, you have two sets, X and Y, that are in F. And X is strictly smaller than Y. Okay. So the idea is that there is always a way to grow X so that you climb towards Y. So formally, there exists a B that is in Y such that X union with the new element B is in F, right? So you can grow towards the bigger set. So this third property is called exchange property. Right. And why it's exchange? It's because, because of the following definition. So before going any further, it's useful to see examples for Metroids. And I think the most natural example of a Metroid is the Metroid of matchings, right? So you have a graph, GVE, and we can define the Metroid of matchings where, the ground set is going to be the edges, and the subsets are just going to be U is a subset of the edges such that U is a matching. Do we want a matching? We can do the matching, I guess. Well, let's not do matching, because in fact matching, I think it's true, but it requires more work. Let's do Metroid of spanning forests. Okay. So right. So the sets. So here again we have a graph. The ground set is the edges, and we take U to be a set of edges is in the Metroid if U induces a forest. Okay. Another way of saying it is that U does not contain a cycle. It's a set of edges that does not contain a cycle. Okay. So let's see the properties, right? So the empty set is of course a valid forest. Well, it doesn't span anything, so it's fine. The second property of monodensity is trivial, right? If something spans, if a set of edges does not have a cycle, then a subset of it does not contain a cycle. The third property is kind of more interesting, right? So let's assume that I have a set X of edges, and I have a set Y of edges, and Y is strictly larger than X, right? Okay, and we would like to argue that there is an edge in Y such that adding it to X would result in a larger spanning forest, right? And the proof is easy, right? Because take X, or relatively easy if you think about it a bit. Take X. X has various trees in it, right? Of course, it might just be every connected component, many of them might just be singleton vertices, but a lot of them are going to be trees in this forest that X introduces, right? Now think about, for every, if a forest have let's call it k vertices, then the number of edges in it are going to be k minus 1, right? Okay, and now the key observation is that now draw the edges of y. Right, the edges of y would be red, right? The edges of y, right? The important thing is that inside a connected component of x, with k minus 1 edges, y can span at most k minus 1 edges, right? It essentially can put as many edges as x can, but no more, right? So first we put in all the edges of y that are internal to the connected component of x, right? But then because y is bigger, there must be at least one edge that is outside those connected components. And just take this edge. This edge must connect two connected components. And clearly, if we add it to x, we get just a forest that with one more edge, which is what we wanted to do. So we have the exchange property. Okay, so let's look at the definition of the Metroid a bit. So a set that belongs to the family F is called an independent set, for a reason that will become clear shortly. The exchange property implies that if we look on maximal sets, right, the largest cardinality sets that are in the Metroid, then they must all be of the same size, right? If there are two different sizes, then you can climb from the smaller one to the bigger one. So they must be of the same size, which is what we know about spanning trees, right? Spanning trees all have the same number of edges. Okay, and I want to talk a little bit about linear Metroids. So linear Metroids are Metroids that come out of linear algebra, And the way to think about it is that you have a ground set U and F, right? But now what we are going to do for every element in U, there's going to be an associated vector, right? Which there's going to be a vector E in some linear space. You know, you can think about this linear space, for example, being RD, right? But in fact, you know, we would usually walk over finite fields, right? So we have a set of vectors, right? Essentially, U is just a set of vectors, and then a subset S of U is in F, if and only if, you know, the set of vectors, right? Vectors E is in S is linearly independent. Okay. So, so we need to first convince ourselves that this is indeed a Metroid. Claim this is a Metroid. Okay. So, you know, the empty set is of course independent, so there is no problem, right? No vectors is a set of independent, linearly independent set of vectors. Second claim that we need is that hereditary, right? If a set of vectors is independent, then a subset is independent, so that's easy. The harder property that requires some thinking is the exchange property. But the exchange property is not very difficult, right? Because think about a set X of vectors, right? So they span a subspace, right? The span of X forms a subset where the dimension of the span, the dimension of this space is exactly the number of, right? This is exactly the size of X. Right? This is the dimension of a linear subspace. Okay, now I give you a dimension Y, a larger set of vectors. Well, and both X and Y are independent, right? Because we are assuming that both of them are in F, right? And Y is larger than X, right? But that implies that not all the vectors of Y can belong to the span of X, because if all of them belong to the span of X, then they must be dependent, because of the definition of dimension of sets of vectors in vector spaces. As such, there exists a Y in capital Y such that Y is not in the span of X. And in particular, we immediately get that X plus Y, which is just the shorthand for X union, you know, Y, right? If we add this vector, then this is linearly independent, right? Because we added a vector outside the span of X. Okay, so this proves that this is indeed a Metroid. Okay, so the rank of a Metroid, maybe I should write it, rank of a Metroid is the size of largest independent set, right? Okay, so and the rank essentially you can think about it as dimension. In particular, one way to represent a linear Metroid is you take the vectors and you write them as columns in a matrix, right? For every element in set U, you're going to have a column that is the vector for this matrix. And now you look on this matrix, and and this is your representation, right? Now the dimension of the matrix, right, it's equal to the dimension of the rows or the dimension of the columns, if you remember your linear algebra, which is the maximum number of independent set of columns, right? So in particular, if I give you such a representation by vectors, you can just apply, since the rank of the Metroid is the linear dimension of the columns, this is also, as I said, equal to the number of the dimension of the rows, and then we can just, move all the rows. We can make the first R rows to be independent, right? Because the dimension, let's assume that R is the rank of the Metroid, right? So we can exchange columns such that, exchange rows so that the first R are independent, and then we can just use regular linear algebra, subtract rows, because this does not affect rank, subtract or add, and with constants on, this does not affect the dimension of the linear space, to make all of this zero, right? Essentially, diagonalization, right? So in particular, we can assume that if we have a linear Metroid of rank R, the vectors are of dimension R, right? Because there only are rows, and in particular, and we can also do diagonalization such that the unit elements are the natural basis of the Metroid. Okay. Okay, the next thing I want to talk about is uniform Metroids. Okay, so a uniform Metroid of rank K is what you would think it is. It's just a subset U, and all subsets S of U such that S is smaller or equal than K, right? Not a very interesting Metroid. It's clearly a Metroid, right? It's hereditary, it contains the empty set, and the exchange property is also immediate. It's a special case, in fact, of a partition Metroid. Now, we want to show that it can be represented as a linear Metroid. So the trick is that, we have n elements. Let's assume that n is the size of U, right? And we're going to work over a field P, where P is larger than n, and it's a prime. Right, so we're working over modulo prime number, and then, we're going to do the natural thing, right? We take the right. We're going to just identify for every element, let's call it I, just for convenience. For element I in U, I'm going to assign it a value AI in GFP, which is non-zero. Non-zero. And unique. Right? And the vector, we now need to define a vector. So VI is just going to be, you don't know, I guess. It's just going to be the representation for this element raised to the power, all the way to the power of k minus 1. So this is a vector in k dimensions, right? So this is good. And now we need to argue that this matrix is indeed has the desired property, right? We want to argue that any subsets of k vectors. So first, it's k dimensions. So if you take more than k vectors, that are dependent. So the largest set in this linear Metroid of size k. But we want to claim that all sets of size k are in the Metroid. And then the claim is not hard to do, because if you write this matrix down, right, you're going to get this A1 squared, blah, 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 A2 squared, right, until AK squared to AK power k minus 1, right? So you get this, this matrix. And this matrix, well, usually it's written with the rows transposed, but it doesn't matter. This is the Vandermonde matrix. Vandermonde matrix. And the important property, of course, is the determinant of this matrix is non-zero. Right? And, you know, I think we already discussed it earlier in the course in the first few lectures. If not, just look it up. It follows from easy linear algebra, right? You know, formally, you know, what maybe I should say it, the determinant is a polynomial, right? So this is a polynomial in those variables, right? The variables are A1, A2, to AK minus 1, sorry, AK, and one can prove that this polynomial has exactly the following form. AJ minus AI, right, so it looks like that. It's this product of polynomial, and in particular, if all the k elements are different, then this is a product of non-zero elements, and since we are working over a field, the product of non-zero element is non-zero. So it's a non-zero polynomial, the determinant is non-zero, which implies that every k elements are indeed independent. So this is the representation of this Metroid. Okay, next stop is graphical Metroids, which we in fact already discussed. So graphical Metroids. Right, so what are graphical Metroids? Well, we already said what they are essentially. The ground, we have a graph, vertices and edges, and we build a Metroid where over the edges, right, right, and you know, S, a subset of the edges, if S is acyclic. Okay, and I already argued that this is indeed a valid Metroid. Okay. Let's see if there's anything else I want to say about this. So the interesting theorem here, so this is theorem 12.2, which is that graphic Metroid can be represented over any field. Right. So this just says that there is a way to write this Metroid as a linear Metroid over a matrix. Right. So the trick is very simple. First, we're going to orient the graph. Orient the graph. Okay. And now write down the incident matrix. Incident matrix. But the incident matrix here is between vertices and edges. So this is V times E. Okay. So and I think here, right, the edges are the columns, because that's what we need for our definition, and the vertices are here, right? Now, what we're going to do for every edge, it's going to be incident to two vertices, right? And now just make the convention that, if it's, of course, all vertices that are not involved with this edge are 0, let's say that this is U and this is V. Right. So, and we're looking on the edge from U to V because we orient them. So, if it leaves U, then we put a 1 there. And if it leaves U, we put 1. And if it enters V, we put -1, right? So every column has 1, 1, and 1, -1, and that's it, right? Now, the nice representation about it is that if you think about it, if you have a cycle in the graph, right, like that, and let's think about the cycle is just oriented in the right direction, then all we need to do is just, if we add up the columns that correspond to it, we're going to get a 0 vector, right? Those vectors are going to be dependent, right? So that's one good direction. And the other direction is, of course, that one way to think about it, if I give you a cycle where the edges are oriented incorrectly, right, like that, then it's not a problem, right? You still take the columns, but every column that is in the wrong direction just multiplied by -1, right? So again, we get that those every collection of edges that form a cycle are linearly dependent, and in fact every superset of them is independent, right? So by the way, a set of elements that is not in the Metroid is called a circuit, right? And minimal ones are called circuit exactly because of this intuition, or because of this application. Okay, so this is easy, but we still want to prove that all acyclic sets are independent in this acyclic sets is independent, right? So the way to think about it is it's by contradiction. Take a set S of edges that is acyclic, right? And assume that there is a linear combination of it. It's in fact linearly dependent. So AI VI, where I is in S, this is equal to 0, right? Okay, but that implies, right, we can take all the, we can take only, we can assume that all the coefficients here are non-zero, right? Because if it's 0, let's just throw it away from S, right? So we are taking the minimal set that is acyclic and is linearly dependent, right? But then, if all the AI are non-zero, and it's acyclic, then there must be an element that appears only in one column, right? But if you take this element that is non-zero, this endpoint, this vector appears only one, there is only one row in the matrix that it appears in, and yet now you add a linear combination. This row in the linear combination of the output vector is going to be non-zero, which is a contradiction. So we are done. We just proved that all sets that contain cycles are dependent, and we proved that all acyclic sets are independent in this linear Metroid. So this linear Metroid is indeed the graphical Metroid of spanning trees. Okay. So this is cute. I guess formally it was a proof, so. Okay, next. Oh, by the way, if we apply this over the field GF2, right? In the above proof I used -1, right? But -1 GF2 modulo 2 is just 1, right? So, so the same proof essentially works if you put 1 and 1 instead of 1 and -1 if you're working modulo 2. Okay. The next creature we want to talk about is transversal network. So to this end we have, I give you a bipartite graph. G equal to U union B, right, and the set of edges E, right, it's a bipartite graph, U, B, and we're going to define the Metroids. The ground set is going to be U, right, the left side, and a subset S of U is in the Metroid if there is a matching that engages S. What do I mean by that? I mean that every vertex in S, right, a pixel subset, there is a matching that uses exactly those vertices on the left, right, and no other edges, right? So essentially it's the intersection, or you can think about it as taking a matching in this bipartite graph and taking its intersection with the left side, okay? And you look on all possible subsets. Okay, so claim. Well, M is a Metroid. Right. Okay, so the two first properties are immediate, right? The empty set is in, and the hereditary property is immediate, because matchings, you can always delete edges from a matching. It's still a matching, but the exchange property is kind of more difficult. So let's assume that I have a set X, right, on the left side, and I have a set Y. Oops, I need a more useful color. And I have a set Y, which might also include the same vertices. That's okay. And this set is bigger, right? Y is bigger than X, right? Size-wise. So you want to prove that there is always an exchange element, right? But this is not very difficult, because what you do, you take that corresponds to two matchings. Right? There is a black matching, which is X, and there is a red matching, which might be like that. Right, there are the same endpoints. I don't know. So there is a red matching. Now, if the red matching have, of course, an edge which is not engaged in the black matching, you can just add it immediately and you get your exchange. So the more interesting cases where this doesn't happen, but now you can use augmenting paths, right? So it's well known that if you have two matching and one is bigger than the other, then there must be an augmenting path from that increases the current matching by 1 if you apply it. And an augmenting path is exactly this exchange set, right? Because think about the augmenting path. An augmenting path looks like that. Right? Let me just draw a short one, right? This is the augmenting path, right? And in set X you have those vertices, right? While the set Y has those vertices, right? Essentially all the vertices of the path, right? So, and those vertices, right? We care only about the vertices that appear in the matching, appear on the right side of the matching, right? But, right, so let's assume that we care, in the set X, so you don't have all the vertices I matched, I lied. You have only the ones that are, let's say, on the left side, right? So you have this and this, but then if you think about it, so now I need to fix my drawing because it wasn't quite correct. So if you think about it, all those red vertices, right, are also in Y, right? So, so you can, right, so you have all the edges in Y, in this path that are in Y, all the vertices of X on this augmenting path belong also to Y, and Y have an extra vertex. And this is your exchange element. So that proves that this is indeed a Metroid. A transversal Metroid. Okay. An interesting property is that those Metroid can be have linear representation. So let me state the theorem. Okay, so the theorem states that you give me a transversal Metroid, right? This graph, bipartite graph, and so on, and matching and so on. So give me this Metroid, then I can represent it as a linear Metroid in a matrix where the numbers are not too large, right? So the numbers are going to be between 0 and x times n times 2 to the n, right? X is just an arbitrary parameter. It's an integer number. So the numbers are, they are exponentially large, but the number of bits they use is small. So it's still going to be polynomial. And the probability of success is at least, this is a randomized algorithm. The probability of success is 1 minus 1 over x. Okay, so by choosing x large enough, you can make this probability arbitrarily large. And the proof, it's one of those tricky, it's not hard, but you kind of have to think in a strange way. So what is going on? We're going to put u in the columns because what else can we do? And we're going to put b in the rows, right? And now the idea is that if there is an edge between u and b, we're going to put a variable there, x. So I have an element, let's call it u and v. You have an element u and v that have an edge. I'm going to put an edge x u v there, right? And that's it, right? So we're going to have quite a bit of variable. Every edge in the graph is going to have a variable. And now the claim, think about before, let me first see what algebraically we need, and then I would show you how to get a matrix. But the idea is essentially now that every one of those variables now, we're going to choose a value randomly from this range, right? 0 to x times n times 2 to the n, right? We're going to just randomly choose a value. That's what will be written there. But to understand why this makes sense, just think about an independent set in this Metroid, in the original Metroid. So the independent set of Metroid, right, we first can restrict ourselves to this set of columns, right? So we have a set of vertices on the left, right, on U, such that there is a maximum matching there, right? Think about all the vertices. So look on this matrix with all these vertices of this column, and what we want to claim is that this matrix has rank, which is the number of columns, right? Now think about the maximum matching. The maximum matching engages vertices on the left, so we can choose those vertices, right? We're going to look on only the submatrix that corresponds to those vertices, right? So we're going to get, let's call them V1, V2 to VR, right? So we're going to have U1 to UR, which are elements on the right, and then we're going to have element V1, V2 to VR here, right? And I'm emphasizing that this matrix is much bigger. There are a lot of other stuff here. But this matrix now is a square matrix, and all we want to argue is that this matrix, that its determinant is non-zero, right? So the determinant in this case, because we have a variable, it's going to be a polynomial, right? It's going to be a polynomial with roughly R square variables, right? And this polynomial is going to be non-zero. That's the critical thing. And the reason is because a determinant is just a sum over permutation, right? Where a permutation picks, you know, entries for every row of the matrix. In particular, a matching corresponds to such a permutation, right? So a matching corresponds to a monomial in this polynomial, and since there is a matching, there is one of the monomials is non-zero, at least one, maybe many more. But if all the monomials are unique, which implies immediately this polynomial is non-zero, and if we choose the values instead of variable, we choose numbers randomly, then it's extremely high probability the determinant is non-zero, which implies immediately that the rank of these R columns is going to be R in the resulting matrix, right? Now we have to kind of go over all possible such, you know, over all such possible submatrices, right? But if you think about it, the number is large, but not monstrously large, right? It's something like n squared choose R maybe. Sorry, not n squared even. N choose R, right? You choose all the, you know, all the subsets of size R. It's bounded by this. This is the maximum, the number of, the upper bound of the number of independent sets, maximum independent set in this Metroid. And now, for each one of them, you just need to pick the number large enough so that the probability is smaller than 1 over this number. And this we get from there is this algebraic lemma that gives us what the range of the numbers need to be. This is the Lempel-Ziff lemma, I think, or something like that. And we are done. Right, so this is a sketch of the proof of this theorem. Okay. Direct sum Matroids. Right, so what are direct sum Matroids? Well, you know, you just have two Matroids, M1 and M2, defined over two disjoint sets. This is, of course, important, because otherwise we get into intersectional Metroids, which is a much nastier topic. So we have two Metroids defined of U1 and U2, and U1 and U2 are disjoint. This is important as I said. Okay, and now we can define the direct sum. I don't see the notation over it. So let's call it direct sum. Direct sum of the two Metroids, M1 and M2. And I guess you probably just use the O plus notation, but okay. And the direct sum is just the Metroid over U1 union U2, where S, a subset S of U1 union U2 is in the Metroid, only if S intersection U1 is in F1 and S intersection U2 is in F2, right? Yeah, so you can just think about it as the cross product Metroid, right? M1 times M2, right? This is really what is going on. And if you take this interpretation, it has an immediate linear representation, right? So if you can represent the Metroid as a matrix, both Metroids over, you have a representation of them as a matrix, then you can just write those two matrices like that, and you get a linear representation of the direct sum Metroids. Okay, so this was direct sum Metroids. The next one are partition Metroids. Partition Metroids, and those are just direct sums of a uniform Metroid. I'm sure that was very enlightening, so let me give more details about that. So here's what's going on. We're going to have sets U1, U2, U3 to UK, and those are uniform Metroids, right? So each one of them has the maximum size, right? A uniform Metroid with rank K means all subset of at most size K, right? So we have rank K1, K2 for all of them. K, let's call it L, KL. And now the partition Metroid essentially is defined over the union of those sets, which of course have to be disjoint. And we take all subset S, defined over the union of the UIs, such that the intersection of S with UI is smaller than Ki, right? You're not allowed to take too many elements from each set. And this is a partition Metroid. Okay, so let's speak about some algorithms for Metroids. And of course, the most natural problem, well, there are many natural problems, but maybe the one that would sound most familiar is the one where we want to find a basis of minimum cost, right? So we have a Metroid, and the elements of U, there is a cost associated with each one of them, right? Now, to remind you, all the maximum independent sets in a Metroid have the same size because of the exchange property. And in particular, we are going to call maximum independent set. We're going to call them bases, just because of the linear algebra connotation, right? So given this cost, for example, I would like to compute the minimum cost basis, right? Where given a set S in F, its cost is going to be, or its weight is going to be just, the sum of the weights of the element in the set. Okay, so it turns out this is one of those rare cases where the greedy algorithm works. And maybe you shouldn't be surprised, right? Because think about the graphical Metroids. So a basis is just a spanning tree of the graph. If we put cost on the edges, then the minimum cost basis is just the minimum spanning tree. And we know that the greedy algorithm works for that, right? So greedy algorithm for mean cost basis. Okay, so how does the algorithm work? Well, we are just going to do Kruskal algorithm, right? We're going to start with an empty set because it must belong to must belong to the Metroid. And now we just, in every iteration, in ith iteration, add cheapest element such that, you know, cheapest element Si, such that the set from the previous iteration Si minus 1, when you add the element Si, is in the Metroid. And that's it, right? And this is exactly, if you think about it, this is just Kruskal, right? Kruskal just say, oh, order the edges in increasing cost and try them one by one, right? And you add them until you get to the first one that it belongs to the, you know, that is defined as spanning tree, and you continue in this fashion, right? And we can do the same thing here, because the important thing is that when the greedy algorithm rejects an element, we are never going to try it again. There is no point, right? If it already cannot be added to the current set, it cannot be added to a later set because of hereditary, right? So theorem, greedy algorithm, maybe I should use a different color just to make things more interesting. Theorem, greedy algorithm computes mean cost basis of Metroid. By the way, I should say that implicitly we are assuming that we have a black box that, given a set, can tell me whether or not it belongs to the Metroid, right? So everything here is polynomial. Okay, so the proof, it's, you know, usual greedy nonsense. So we're going to look on the optimal basis, and we're going to order the element O1, O2, O3 to O, I don't know, let's assume the size of the basis is M, right? This is the optimal basis, and I'm going to assume that this is a monotone increasing ordering. M of W1, the cost of the first element is smaller than the cost of the second element in the optimal solution, and so on. This is optimal. Optimal, and OI is just the suffix, the prefix. And now, of course, we already defined the set Si, which was this, the greedy algorithm. Pick two element S1 to Si, right? And the critical claim is, of course, that the cost of capital Si is smaller than the cost of optimal I for all I. And if this is true, then we are done, right? Because clearly the algorithm would end up with a basis, because we are adding elements until we cannot add any more elements. So, and all the bases have the same size, so we're going to end up with a basis. And this would imply that this is the minimum cost. And the proof, it's not too difficult, but let's see if I can do it. So let's look on the first I elements of OI and SI, right? And then let's not look on the last element, right? So we have the prefixes. Okay. And now the key observation is that Si minus 1, right, the first I minus 1 elements, this is cheaper than OI minus 1, right, because of induction. By the way, the condition trivially holds for empty sets, right? So in the beginning it holds. So okay, so the purple is cheaper, Si minus 1 is cheaper than OI minus 1. Okay, but now we're going to use the exchange property, right? Si minus 1, there is an element Si minus 1 is smaller than OI, right? One is I minus 1, the other one is this is I minus 1, this is I. So by the exchange property, there must be an element in the set OI that we can add to Si minus 1, right? So there exists an element, there exists, let's call it OI prime. There exists OI prime in OI such that Si minus 1, if we add OI prime to it, this is in the Metroid, right? But clearly the cost of this set, W of this new thingy, Si minus 1 plus OI prime, well, you know, the cost of AI prime is going to be smaller than the cost of OI. So this is smaller than the cost of Si minus 1 plus the cost of OI, right? Because OI is the most expensive element in the optimal set, but that by induction is smaller than the cost of OI minus 1 plus the cost of OI, which in turn is the cost of OI, right? So the optimal solution with our element is more expensive than this candidate solution, but of course the candidate solution, the cost of SI is of course smaller than this cost because we are taking the best cost out of all candidate such solution, right? So as such, this is smaller than W of OI, which proves the induction. And now we are done. So the greedy algorithm in this case works, and we are happy. This is literally the proof for the MST algorithm. Sorry about all the beeps. Okay. What's next? So let's see what's next. Okay, so right. Okay, so of course, to remind you, a circuit is a set that is not independent set, or to be more precise, it's a smaller set that is not independent set. And of course, it's natural to ask is, can we compute circuits? Can we compute circuits? Right, minimum weight circuits, for example. Right? We already showed that we can compute the minimum weight basis, which of course, by the way, immediately lead to maximum weight basis. It's essentially running, you know, sorting. If you think about Kruskal, just sorting the edges in decreasing order. So, so can we compute the minimum cost circuits, right, efficiently? Now, one needs to be careful because for the graphical Metroid, of course, computing the minimum weight circuit is finding the minimum cost circuit in a graph, and of course, this is easy, right? So compute mean cost circuit in the graphical Metroid. This is just computing a circle. So for graphical Metroid, it's easy. Right. Graphical Metroid, the answer is yes. For graphical Metroid, we can do this. Okay, because it's just finding the shortest circuit in a graph, right? Right. The easiest thing to just remind you, the easiest, laziest way to do it is you take a graph, you remove an edge, and you compute the shortest path between the two endpoints of the missing edge in the remaining graph, and you do it for every edge, and you return the minimum one found. Right? It's kind of not very efficient, but it would work. It's definitely polynomial. Okay, but on the other hand, computing maximum cost circuit in a graphical Metroid well, what is it, right? If you think about it, so so if we set it up in the right way, this is just going to be computing an Hamiltonian cycle, right? And so this problem is in fact NP hard, right? So computing maximum circuit in a Metroid is definitely maximum size circuit is definitely okay. So now I have to be very careful, right? Because I think what I said is not quite correct. So let me be careful. Okay, so one has to be a bit more careful than I've been, so let's try to do it. Circuits are sets that are not in the Metroid, but they have to be minimal, inclusion minimal. So circuit in a graphical Metroid as such corresponds to a cycle in the graph, right? And as such, asking if there is a circuit in the Metroid with n elements correspond immediately to is there a Hamiltonian cycle in the graph of size n. Now, for the case of minimum circuits, right? So the graphical Metroid is not going to give this to us. We need to use something else, right? So we need to use this problem called even set. So in even set, you need to find, you have a set system, and you want to find a subset such that for any set in the system, x intersection with s is an even number. And of course, you have to require that x is not empty, because otherwise there is a trivial solution, right? So this problem is known to be NP complete. I didn't immediately see how to prove it, but it shouldn't be too difficult. A famous last word, I guess. But let's assume that this problem is NP complete, and then it's pretty easy to show that this is equivalent to finding smallest circuit in the natural Metroid, in the natural associated Metroid, in the Metroid, right, where you use Metroids over G2, over GF2. Right? And the reason is because every row in the matrix is going to be a set, right? The elements are, of course, columns, right? And a circuit is just a non-trivial linear combination of the columns such that modulo 2, they're all even, right? That's exactly equivalent to just choosing the set X, the element of the set X. So the two are equivalent, and as such, finding a smallest circuit here is NP hard or NP complete, depending on which version you prefer. So since both finding smallest circuit in a Metroid and finding largest circuit in a Metroid are NP hard, it's natural to ask about the fixed parameter tractability of those problems. And in particular, it's known that right? So the question is there a circuit of size k? So going back to the Metroids for matching, right? The bipartite Metroid for matching, right? We can ask, is there a circuit of size k? Well, what does this mean? It means that there are k elements on the left side such that there is no matching for them, right? This is exactly what it corresponds to. And by Hall theorem, that just says that there is a set S of U such that the neighboring set of S is of size k, and neighboring S is smaller than k, right? So it turns out that this is a W1 hard problems. Which is very surprising at some level because, of course, we can find such a set, right? We can compute the maximum matching and using flow, whatever. And if we are not at the maximum flow or a perfect matching, we can find this counter set, right? Set that shows that you cannot do any better. But here we're asking for a specific set that shrinks of size k, and that turns out to be much harder. So this is kind of pretty surprising. By the way, it is not currently known if there is an FPT algorithm for even set, which means that, is there a set of size k such that is solution for the given instance of even set, which is equivalent in terms of is there a circuit in a binary Metroid of size k. Okay, this is all I wanted to say today, and we will continue in the next lecture. Thank you.